On the 17th of March, 2025, a Freedom of Information Act request was filed with the Central Intelligence Agency. The subject: any and all documents, communications, or intelligence assessments related to the interstellar object, designated 3E Atlas. 6 weeks later, the reply arrived. 4 sentences. No attachments. The agency stated it could neither confirm nor deny the existence or non-existence of records responsive to the request. This language, known as a GLOMAR response, is typically reserved for matters touching national security, covert operations, or classified surveillance programs. For an object that NASA had already publicly classified as a natural comet, the phrasing was unexpected, unusual, and to some observers, deeply unsettling. The scientific community took notice. Dr. Avi Loeb, the Frank B. Baird Jr., professor of science at Harvard and chair of the Galileo Project, remarked in an interview that institutional silence around cosmic phenomena often reflects not secrecy, but a cautious alignment between observational uncertainty and policy frameworks designed for terrestrial threats. Yet he also noted that when intelligence agencies decline to discuss objects entering our solar system from interstellar space, it invites questions about what data streams exist beyond public telescope. What sensors, what orbital platforms, what classified spectrographs might be watching the sky in wavelengths we do not see published in journals. NASA's tracking data showed a clean hyperbolic trajectory. Breakthrough Listen's radio scans from Green Bank on the 19th of December, 2025, detected no narrowband signals, no coherent transmissions, no technosignatures of any kind. Every empirical measure pointed to a natural object, and yet the silence lingered. Not because the data suggested otherwise, but because silence itself, in the context of cosmic visitation, becomes a kind of signal, a shadow in the metadata, a question left open at the edge of what we are told and what we are allowed to know. This is not a story about aliens. It is a story about a comet, but it is also a story about how we respond when something arrives unannounced from the space between stars, carrying with it dust older than our sun, ice formed in the cold disks of distant planetary systems, and a trajectory that has never been bound to our gravity. If you find yourself drawn to these questions, to the intersection of data, mystery, and the vast quiet of the cosmos, then stay with us. Because what we are about to explore is not fantasy. It is something stranger. It is real. Whoop. The first detection came on the 1st of July, 2025. It was a Tuesday. The Atlas Survey Telescope, stationed at the Cerro Tulalo Inter-American Observatory in the Chilean Andes, was conducting its nightly sweep of the southern sky. Atlas, the Asteroid Terrestrial Impact Last Alert System, was designed by NASA to catch near-Earth objects weeks or months before potential impact. Its 4 wide-field cameras scan millions of square degrees each night, comparing each frame against reference images to detect anything new, anything moving. At 3:14 Universal Time, the system flagged a faint streak in Centaurus. Magnitude 18.3. Moving fast. The automated pipeline tagged it as a potential comet and forwarded the alert to the Minor Planet Center in Cambridge, Massachusetts. Within 6 hours, the Zwicky Transient Facility at Palomar Observatory in California had slewed to the coordinates and confirmed the object. By midday on July 2nd, amateur astronomers in Australia and South Africa had captured it with backyard CCD rigs. The light curve showed a distinct coma. A tail was forming, but the motion was wrong. Not elliptical, not parabolic, hyperbolic. The orbit integration showed an eccentricity above 1.0. That meant it was not native to the solar system. It had come from somewhere else. The Minor Planet Center began issuing electronic circulars. Observatories around the world responded. Within 72 hours, researchers had combed through archival sky surveys, a process called precovery, and found the object in images dating back to late May. Those earlier detections extended the observation arc and tightened the orbital solution. By the 8th of July, the International Astronomical Union officially designated it C2025 None and gave it the shorthand 3I Atlas. The AI prefix marked it as the third confirmed interstellar object in human history. The first was Onai Oumuamua, discovered in October 2017. The second was Toabi Borisov, found in August 2019. Both had sparked intense scientific interest. Both had raised questions. And now, just 6 years later, another visitor had arrived. The orbital elements were striking. Eccentricity, 1.026. Inclination, 8.7 degrees relative to the ecliptic plane. Perihelion. Its closest approach to the Sun would occur on the 29th of October, 2025, at a distance of 0.64 astronomical units, well inside the orbit of Venus. Its closest approach to Earth would come later, on the 19th of December, at 1.820, roughly the distance between Earth and Mars at opposition. Safe. Distant. But close enough to resolve fine structure with our best instruments. What made 3 Atlas extraordinary was not just that it came from beyond. It was that we could watch it unfold. Most comets are discovered months before perihelion. This one gave us 5 months. 5 months to mobilize telescopes, to coordinate campaigns, to gather data across every wavelength we could muster. And the world responded. The observation campaign began in earnest in late July. Gemini North, the 8-meter telescope on Mauna Kea in Hawaii, obtained deep imaging in multiple filters, resolving the coma structure down to sub-arc-second scales. The images showed a dense, nearly spherical coma surrounding a faint nucleus, with a faint tail extending westward. By mid-August, the 2-meter twin telescope at Taita Observatory in Tenerife had captured time series photometry, tracking brightness variations over consecutive nights. The data revealed periodic modulation. The comet was rotating, and the jets were not symmetrical. Hubble Space Telescope turned its wide-field camera 3 toward 3I Atlas in early September. The resolution was exquisite. The coma showed concentric shells, dust structures ejected in discrete bursts, likely tied to the rotation of the nucleus. The tail displayed striations, narrow lanes of brighter material interwoven with darker voids. These features suggested episodic outgassing, driven by regions of varying ice composition exposed to sunlight as the nucleus spun. The rotation period, estimated from morphological changes and photometric curves, came in at approximately 7.3 hours. Fast, but not unprecedented. NASA's Parker Solar Probe, orbiting the Sun closer than any spacecraft in history, provided an unexpected vantage point. Its wide-field imager for a solar probe, or WHISPER, captured 3I Atlas from an oblique angle during its inbound pass in late September. The images showed the tail stretching more than 2 degrees across the field of view, a gossamer structure sculpted by radiation pressure, and the magnetic tension of the solar wind. Frame by frame, over a span of 11 days, the tail evolved. It thickened. It twisted. Dust grains released weeks earlier were still moving outward, tracing the object's path through the inner heliosphere. The James Webb Space Telescope observed 3IS on the 9th of October, using its near-infrared spectrograph. The spectrum was revelatory. Strong absorption bands at 427 microns indicated carbon dioxide ice. Weaker features near 2.7 microns suggested water ice, though not as dominant as in solar system comets. There were hints of organic compounds, complex carbon chains formed in cold molecular clouds, but the signal-to-noise was marginal. What was clear, however, was that this comet had formed in an environment rich in volatile ices, likely in the outer regions of a protoplanetary disk around a distant star. Amateur astronomers contributed continuously. CCD stacks from observers in Japan, Italy, New Zealand, and the American Midwest filled gaps between professional campaigns. Photometric measurements poured into the Comet Observation Database, a collaborative archive maintained by the Minor Planet Center. Each observation added a point to the light curve, refining the rotation period, constraining the dust production rate, mapping the asymmetry of the coma. NASA's Punch mission, the polarimeter to unify the corona and heliosphere, began routine imaging in late October, just after 3 Atlas passed perihelion. Punch is designed to study the solar wind, but its wide-field coronagraphs also track comets. The images captured the tail extending beyond 5 degrees, over 10 million kilometers, a river of particles streaming away from the sun. Time-lapse sequences showed waves propagating through the tail, density fluctuations driven by gusts in the solar wind. And then there was Green Bank. The Robert C. Byrd Green Bank Telescope, the largest steerable radio dish on Earth, observed 3IS on the 19th of December, 2025, during its closest approach to Earth. This was not a casual observation. It was part of Breakthrough Listen, the most comprehensive search for extraterrestrial intelligence ever undertaken. For 6 hours, the telescope scanned frequencies between 1 and 12 gigahertz, listening for any narrowband emission that might indicate a signal, a beacon, a transmission. The data were processed in real time, searching for drifts, pulses, modulation patterns. Nothing. The comet was silent, radio quiet, exactly as expected for a natural object. And yet, the observation was made. Because we had to know. To understand 3I Atlas, we must first understand what a comet is. At its core, a comet is a remnant, a frozen archive of the primordial solar nebula, preserved for billions of years in the cold outer reaches of a planetary system. The nucleus is a mixture of water ice, carbon dioxide, ice, methane, ammonia, and dust. Silicate grains, organic molecules, perhaps even prebiotic compounds. When a comet approaches a star, solar radiation heats the surface. Ices sublimate directly from solid to gas, carrying dust particles with them. This forms the coma, a temporary atmosphere that can grow larger than Jupiter. The gas and dust then stream away, shaped by two forces: radiation pressure from starlight, which pushes dust into a curved tail, and the solar wind, which ionizes gas and stretches it into a straight, narrow plasma tail. For 3I Atlas, the process was the same, but the composition was different. The dominance of carbon dioxide over water suggested formation beyond the snowline of its parent star, but closer in than the methane ice line. This places its birthplace in a region analogous to the Kuiper Belt, but in another solar system. The spectroscopic data from WST indicated a COMHO production rate of roughly 200 kilograms per second at perihelion. Water production was lower, perhaps 60 kilograms per second. Dust production, estimated from the brightness of the tail and scattering models, was around 100 kilograms per second. These numbers, dry and precise, tell a story of sublimation, of energy transfer, of a small icy body slowly disintegrating under the heat of an alien sun. The jets were particularly interesting. High-resolution images from Gemini and Hubble showed at least 3 distinct jets emanating from the nucleus, each aligned with a different rotational pole. The jets were not steady. They brightened and dimmed over the course of hours, tied to the rotation period. One jet, unusually, pointed almost directly toward the sun. This created what astronomers call an anti-tail, a forward-pointing structure that appears to defy the physics of radiation pressure. But it does not. It is an illusion of geometry. When dust is released from the sunward side of the nucleus, it initially moves forward in the comet's orbital path before radiation pressure bends it back. Seen from Earth, at certain angles, this dust can appear as a spike pointing toward the sun. 3 Atlas displayed this feature prominently in early November, and it wobbled. Night to night, the angle shifted slightly. The jet was precessing, likely due to non-uniform outgassing torquing the nucleus. The orbital dynamics were equally telling. The hyperbolic trajectory, with an eccentricity of 1.026, meant the comet was moving at 3.7 kilometers per second relative to the sun at perihelion, far faster than any bound object. Its inclination of 8.7 degrees placed it nearly in the plane of the solar system, an unusual geometry for an interstellar interloper. Most objects entering from the galactic field should arrive at random angles. The low inclination suggested a trajectory aligned, by chance or by history, with the ecliptic. Whether this was coincidence or the result of gravitational deflections during its journey through the Oort cloud of another star system remained an open question. But not everything fit cleanly. The anti-tail wobbled more than models predicted. Dust dynamics simulations, run at the University of Maryland and the European Space Agency, struggled to reproduce the exact morphology without invoking unusually large dust grains or bimodal size distribution. The rotation period derived from photometry, 733 hours, did not perfectly match the periodicity seen in jet morphology, which hinted at a secondary spin axis or a tumbling motion. This is not unknown in comets, but it added complexity. The light curve showed episodic brightening events. On the 14th of November, the brightness increased by 0.4 magnitudes over 6 hours, then returned to baseline. No outburst was detected in gas emission, only dust. This suggested a sudden release of material, possibly from a fractured surface layer, or a collapse of a subsurface cavity, warmed by conducted heat. Another brightening occurred on the 3rd of December, smaller but still measurable. Each event left a temporary shell in a coma, visible in high-cadence imaging from amateur networks. The orbital eccentricity, while confirming an interstellar origin, was unusually close to unity. Most ejected objects from other star systems should have higher excess velocities, implying eccentricities well above 1. The relatively low hyperbolic excess, just a few tenths above 1, suggested either a very gentle ejection from its birth system or a recent gravitational encounter that altered its velocity. Statistical models, run by researchers at the Harvard-Smithsonian Center for Astrophysics, found the low inclination and low excess velocity to be a rare combination, occurring in less than 2% of simulated interstellar trajectories. Rare does not mean impossible, but it does mean interesting. There were also the radio observations. Not the breakthrough listen scan, which was silent, but earlier Very Large Array observations in October that detected faint continuum emission at 3 centimeters. This is expected from thermal radiation from dust, but the flux density was slightly higher than models predicted for the estimated dust mass. Some researchers proposed that the dust grains were unusually porous, with fractal structures that increased their effective cross-section. Others suggested a population of small icy grains still sublimating in the coma, contributing millimeter wave emission. The data were not conclusive. The signal was faint, noisy, at the edge of detectability, but it was there. None of these observations suggested anything beyond natural physics, yet each added a layer of nuance, a wrinkle in the interpretation. Science thrives on such wrinkles. They are where discovery begins. The interpretive landscape is wide. The baseline model, a Kohn-rich cometary nucleus ejected from another planetary system, explains the majority of observations. The coma, the tail, the jets, the rotation, the spectrum, all consistent with natural sublimation and dust dynamics. The low water-to-Ka ratio suggests formation in a colder region than most solar system comets, possibly around a low-mass star where the water ice line was closer to the host. The hyperbolic orbit confirms it as a visitor, passing through, never to return. But scientists are trained to ask, what else could fit? Some researchers have explored whether the nucleus might be unusually porous, a loosely bound aggregate of icy pebbles, which would explain the episodic outbursts and the high dust-to-gas ratio. Others have modeled heterogeneous surface compositions, where patches of pure cone ice alternate with water-rich regions, driving asymmetric jets and complex rotation. These are refinements, not contradictions. There are less conventional discussions as well. A small subset of researchers, including Dr. Loeb, have argued that interstellar objects warrant exhaustive technosignature searches precisely because they are so rare. The logic is Bayesian. If even a tiny fraction of interstellar objects were artificial probes, the discovery would be transformative, and the cost of searching is low. The breakthrough listen observation was part of this philosophy. It found nothing, but the absence of evidence is also data. It constrains the probability. It narrows the parameter space. Others have examined the orbital geometry through the lens of galactic dynamics. Could 3I Atlas have been gravitationally focused toward the solar system by a past close encounter with a rogue planet or brown dwarf? Could its trajectory encode information about the density of unseen mass in the local interstellar medium? These questions push into speculative territory, but they are grounded in calculable physics. They are hypotheses that can, in principle, be tested. The key is proportion. Extraordinary claims require extraordinary evidence. The evidence we have points overwhelmingly to a natural object. But the questions remain valuable. They keep us looking. They keep us measuring. They remind us that the universe is under no obligation to be simple. 3i Atlas is now leaving. By late January 2026, it had passed the orbit of Mars, fading to magnitude 21.I. Ground-based telescopes have lost it. Hubble may capture it once more in March, if observing time is allocated. By mid-2026, it will cross the orbit of Jupiter, moving outward at nearly 40 kilometers per second relative to the Sun. In a decade, it will be beyond Neptune. In a century, beyond the heliopause. In 10,000 years, it will be light years away, traveling through the interstellar void once more, perhaps never again to encounter a star. But we are not done watching. The Vera C. Rubin Observatory, now operational in Chile, will begin its legacy survey of space and time in late 2026. Its 8.4-meter mirror and 3.2 gigapixel camera will scan the entire southern sky every few nights, detecting objects 100 times fainter than current surveys. Simulations predict Rubin will discover dozens, perhaps hundreds, of interstellar objects per year. 3. Atlas will be the first of many. Each new visitor will add to our statistical sample. Each will refine our understanding of ejection mechanisms, of interstellar space weathering, of the diversity of planetary systems across the galaxy. Radio surveys are expanding. The square-kilometer array, under construction in Australia and South Africa, will offer unprecedented sensitivity for technosignature searches. The next interstellar object will be scrutinized not just optically, but across the electromagnetic spectrum. Infrared, ultraviolet, X-ray. We will watch for thermal emission, for fluorescence, for any signature that deviates from expectation. There are even concepts for interception. The Comet Interceptor mission, planned by the European Space Agency for launch in 2029, will wait at the Earth-Sun Lagrange point 2, ready to redirect toward a newly discovered long-period comet or interstellar object. If another 3i arrives with sufficient warning, we may send a spacecraft to meet it, to fly through its coma, to taste its dust, to bring pieces of another star system back to Earth. The science is iterative. Each observation refines the model. Each anomaly suggests a new test. Each visitor teaches us something we did not know. And slowly, across decades, the picture sharpens. There is a particular kind of humility that comes from watching something pass through our solar system that was never ours to begin with. 3 Atlas formed around a star we cannot name, in a disk of gas and dust that collapsed and dispersed billions of years ago. It was ejected, perhaps by the gravity of a giant planet, perhaps by the tidal pull of a stellar companion, perhaps by the slow diffusion of objects in a crowded planetary system. It drifted through the galaxy, through clouds of hydrogen, through magnetic fields, through the dark. And then by chance, by the geometry of orbits and velocities, it fell toward our sun. We saw it for 6 months. We measured it. We photographed it. We listened to it. And then it left. The CIA's non-committal reply to the FOIA request will likely never be explained in detail. Such responses are procedural, legal, designed to protect sources and methods, not to stoke mystery. But the juxtaposition remains. A cosmic visitor, observed by hundreds of telescopes, analyzed by thousands of scientists, declared natural by every empirical measure. And yet, an institutional silence that invites questions. Not because the data are ambiguous, but because we are human. Because we wonder. Because the idea that we might not be alone, that we might one day find evidence in the trajectory of a comet or the spectrum of a distant signal, is too compelling to dismiss without looking. 3 Atlas does not give us that evidence. It gives us dust. It gives us ice. It gives us physics. And that is enough. Because every interstellar object, every distant comet, every hyperbolic trajectory expands the map of what we know. It tells us that planetary systems eject debris, that the galaxy is filled with wanderers, that the space between stars is not empty, but seeded with the remnants of creation. We will see more. We are building the instruments. We are training the algorithms. We are watching the sky. And when the next visitor arrives, we will be ready. Not with fear, not with fantasy, but with telescopes, with spectrographs, with patience, with the quiet, determined curiosity that has always been humanity's greatest tool. The cosmos is vast. The questions are endless. And the data, always, will guide us home.